I'm very honored to introduce Liz Rice.
Hi, I'm Liz Rice from Aqua Security. And in this beginner's guide to eBPF programming, I'm going to be writing the eBPF equivalent of Hello World. But before we get to that, let's talk about some of the things that are happening when we run an eBPF program. So you probably know that eBPF lets you run your own custom code in the kernel. Normally, our application code runs in user space, and if it needs the kernel to do something, a privileged action on its behalf, then the application uses a system call to make that kind of request. Normally, system calls are abstracted away. Most programming languages hide the system call interface from us. If the application wants to interact with an eBPF program, it makes sense that there is a system call, and indeed there is, and it's called BPF, that allows our user space application to communicate with the kernel about this eBPF program that we want to run. And that system call is called BPF, and we can look at the manual page to find all sorts of good information about eBPF programming. eBPF programs that are going to run in the kernel are typically written in C and then compiled into eBPF bytecode. They're quite restricted in what they can do because this code running in the kernel has to be safe to run. It can't crash, it can't get into an infinite loop, so it's going to get verified before it's allowed to run. Our eBPF code running in the kernel has access to some helper functions that allow us to get information about the current system. I'm going to be using these functions here to trace out debugging messages and to get the current user ID. I'm also going to be using a map. So maps are data structures that we can use to communicate information between the eBPF program running in the kernel and our user space application. And the last thing we need to know is that our eBPF program is attached to some kind of event. Whenever that event happens, that triggers our eBPF program to run. You might have come across BPF trace, which is a higher level abstraction for running eBPF code. And I'm just going to use this to show you those BPF and a couple of other system calls that happen when we run eBPF code. So I'm going to take one of those examples from the BPF trace README, and I'm going to run that. It doesn't really matter what this is doing. I'm going to use strace to look at the system calls as they're invoked, and I'm interested in the BPF system call and a couple of others. Okay. So we can see these system calls that get invoked. We can see quite a few BPF ones doing things like loading a program, creating a map. So there's a few of those. And also here, we can see the system calls that are used to associate a program with an event. In this case, it's a trace point event, and it's got ID 7. Here's our program that's been loaded, and it's got ID 8. And this IO control call here associates the event 7 with that program with identifier 8. That's now going to get triggered every time that event occurs. Okay. So just recapping what we saw eBPF programs getting loaded into the kernel. We saw maps being created, and we saw how our BPF program can get associated with an event. So I think we know enough now to write our Hello World program. So I'm going to use BCC, Python framework that makes it very easy to write an eBPF program pretty quickly. And I need to do it pretty quickly because time is limited for this talk. And BCC, in particular, one thing it does is it takes care of the compilation for me. So I just give it my C program in the form of a string here in my Python code, and it's going to compile it for me. So in my C code, I'm going to write a function called hello world, and I'm going to use that helper function that we saw. Oops. To print out, of course, hello world. This is C, so I have to remember my semicolons, and we return 0. So BCC takes a lot of the heavy lifting away, but I need to attach my program to an event. And I would like to trigger my program every time a new process gets created on the system. That's called a clone. And I'm going to use a kprobe event. So kprobe gets triggered when on the entry to a function in the kernel. And I need to know what the kernel function is that gets invoked when we clone a new process. And there's a nice way to find this, which is get the function name for a syscall. So whenever a clone syscall happens, that's going to be the name of the kernel function that gets invoked. And I can associate that event, which is clone. Whenever that happens, I want to invoke the function called hello world. And the last thing I need to do is just make sure we trace out whatever kernel writes up here. Okay, let's give it a try. Okay, so nothing has collapsed yet, nothing bad has happened. So let's start cloning some new processes. Every time I run a program, a new process gets cloned, and we can see hello world. All right, let's add something to this. How about we trace out the user ID? So whatever the user is that causes a new process to be cloned, I want that to be shown as part of my tracing up here. And there was a BPF helper function for that. Get current UID GID. Now, this is going to give me a 64-bit result, but the group ID is in the top 4 bytes and the user ID is in the bottom 4 bytes. So 2, 3, 4. I'm only interested in what's in the bottom 4 bytes. And let's trace that out. Okay. Run that. And we create some new processes, and we can see that triggered with ID 1000. Let's check what my user ID is, and it is indeed 1000. But let's do sudo. So I get the sudo process is going to be invoked by my normal user, then that's going to run as root. So I should see a process with the ID 0. And indeed, that's what we see. So that's all happening as expected. Now, this trace printk is fine for hello world, but it's not good for production applications because it writes to a single pipe. This reads from a single pipe. That's not really going to scale if we want to run multiple eBPF programs. So instead, we're going to use a map. BCC makes it very easy to use a map, and there are lots of different types of map. I'm going to use a hash table. and that has key value pairs. I'm going to keep a counter of how many times each user clones a new process. So my key is going to be the user ID, and the value is going to be a counter. So I'm going to create my hash table and call it clones. And I want a counter, which would be 0 if, well, the first time, we'll initialize it to 0. And I'm going to need a pointer P. So we get the current user ID, and then we're going to look up in this hash table, look up the current value associated with this user ID. Now, this is actually a pointer, and before I can dereference it, I have to check that the pointer is not 0. And if it isn't 0, then we can get the counter value. If it is 0, that's because there isn't an entry yet for this user ID. So having the counter initialized to 0 is appropriate. If it's non-zero, we get whatever the current value is associated with that user ID. And then we increment the counter and we update the value associated with that user ID with the new value of the counter. Okay. The other thing I need to do is change my user space code so that instead of just reading out of the trace print pipe, it accesses the data in this data structure. Again, this is something that BCC makes very easy. So I don't have to write a lot of code to get those key value pairs out. This is going to loop, and every 2 seconds it's going to print the current state of my hash table. Okay, so let's run that. And there aren't any entries to start with, as expected. But if we start cloning some new processes, we can see the entries. And we can create an entry for the root user as well. And there it is. So we've been able to extract data from the kernel, the eBPF program running in the kernel, and see it in our user space application. So I think we should just recap what we've seen here. So our eBPF program, written in C, gets compiled into an object file. And that object file includes the eBPF bytecode and definition of the maps that we're going to use. Then our user space application makes BPF system calls to load the program into the kernel and to create those maps that we're going to use. Then the user space code attaches that BPF program to whatever event it wants to trigger using the perf event open and IO control system calls that we saw earlier. And then it can read and write to those maps using these BPF map operations. I hope that gave you an insight into what it is to write an eBPF program and what's happening in both user space and in the kernel when we run eBPF programs. There's some more information on my GitHub, including a reference to a longer version of this talk that dives into a few more details. And if you have any questions, do just get in touch. Thanks very much.
Thank you very much, Liz.
Hi.
What an amazing presentation to kick us off and get us started into the summit. Please give Liz a virtual round of applause in the Slack channel. Unfortunately, we can't hear it, but at least you can see it. And also please wave in the Slack channel so everybody can see who you are to ask questions.
Yeah.
Let's see if questions are popping in. I can see the applause. Maybe to kick us off, here's the first one for you, Liz. You have been involved in many open source communities. From your perspective, what is unique about the eBPF community from a community and technology perspective?
Oh, that's a difficult question. So I think, I mean, it feels to me like it's it's a low-level technology, and yet it seems, at least at this point in time, like a lot of people who are involved are keen to embrace people into this world. I think, if we think about perhaps Linux kernel development traditionally, it has looked very scary to a lot of people outside of that community. But I think eBPF is moving in the right direction to be welcoming, even though it's quite hard tech. So well done, everyone who's getting involved.
Awesome. We have one more question here. Can you suggest some tools to debug eBPF programs?
Oh, I think there's probably going to be some people who are better placed to answer that than me, like Thomas, for example. For the experimentation that I've done, I found things like strace, where I've just been trying to figure out what's going on, super useful. And I will also shout out for a tool that my team are working on called Tracy. I think they're going to be doing a lightning talk on that tomorrow, but that's kind of interesting in terms of exposing some other interesting events. I'm not sure that's a great answer to that particular question, but
I think it is, and I think we'll hear lots of lightning talks and several keynotes on other additional topics on how to debug eBPF programs as well. We had one more question, which is also a bit technical, but can you dereference null pointers in eBPF code?
Good. It's a good question. Yes, you have to check that you're not dereferencing a null pointer. Every time you have a pointer, you have to check that it's non-null. If you try to load a program that doesn't explicitly check for non-null, which is valid C in the normal world, it would just crash. But the verifier will prevent that from being loaded. So you got to do that check for non-null.
Exactly. Yeah, I think we'll have Alexei go into a lot more details on the verifier and the security aspects of eBPF. I see several other questions in the same context. Is eBPF program okay from a compliance or regulatory perspective? I think that's going into the same direction. If I write my own kernel driver that collects some profiling data, could I access the data via eBPF, via my eBPF program? Maybe that's an interesting question. So I will ask it again. If I write my own kernel driver that collects some profiling data, could I access the data via my eBPF program?
I think that's so eBPF, to my understanding, and there are probably, again, people better qualified than me, but eBPF programs get access to those maps, and you're going to have to use that kind of data structure or helper functions that let you get access to other information. If you have a way to get your kernel driver to insert data into that map, then go for it. Yeah.
Yep. I think there's one more interesting question here, which is why does eBPF need root privileges? Why do you need privileges to run eBPF programs?
Yes, so it needs certainly capsysadmin is a capability that is required. I'm not sure if there is another more granular capability, but you need privilege to load that eBPF program into the kernel. Basically, you can't call that syscall if you don't have that capability. So yeah, you pretty much have to run as root or with capsysadmin.
Exactly. There is this unprivileged BPF mode, which is typically disabled, and it is possible to load programs without privileges, but it will be a much more restricted runtime of eBPF, and it's primarily targeted at like profiling use cases, and will have much less privileges in terms of what it can access from a system perspective. I think this was, again, a fantastic presentation. Again, give a round of applause to Liz.
Thank you very much.